All right, so now we're going to talk a little bit more about the quantitative aspect of solution chemistry, and that's this idea of concentration. The main concentration unit that we use is molarity. We remember molarity is defined as the moles of solute, so whatever we've dissolved into our solvent, per liter of solution. So it's just simply a ratio of amount of solute per some amount of our solution. Now when we're dealing with molarity, we can use it for a couple different things, right? We can use it as a conversion factor between those two things, liters and moles or moles and liters, going back and forth. Okay, so that's the first thing we can do, right? We can use it as a conversion factor from volume or liter to moles or moles back to liters. Okay, so for example, let's say we wanted to find out how many moles of magnesium chloride are in 1.50 liters of 0.4 molar magnesium chloride. Okay, so we see, okay, we have an amount, a volume, and we have a molarity. So I can take, well, this is my measured value, right? When we deal with solutions, our measured value is volume. We're dealing with like solids or gases, right? Our measured volume may be the mass. Okay, so we have, our solution has 1.5 liters. We want to find out how many moles of magnesium chloride do I have? Well, I can see we can use our molarity as a conversion factor there, right? We have 0.4 molarity of our solution, and so that would be 0.4 moles of magnesium chloride per 1 liter of solution. So now we see we can convert from volume in liters to moles, and so we would see we end up getting 0.600 moles of magnesium chloride. Okay, so that's one thing that we can look at, is the amount of moles of this specific compound. Secondarily, what we can do is we can look at, well, what if we have a solution? How many ions do we have? What's the concentration of our ions? Okay, so we can look at the concentration of ions. So let's say we want to find out the concentration of potassium ions. So remember, brackets means concentration and molarity, in a 0.900 molar potassium phosphate solution. Okay. So now if we go and we look at, well, what is this? What are we trying to do, right? We have a concentration of the overall compound. Now we know potassium phosphate is not going to stay stuck together as potassium attached to our phosphates. We see that we have our potassium phosphate is going to break apart to 3 potassium ions and a phosphate ion. So that would mean for every single potassium phosphate, we get 3 potassium ions. Okay, so if we have 0.9 molarity K3PO4, potassium phosphate, we can go ahead and say, well, we would have 3 moles of potassium for every single mole of potassium phosphate. And so that would tell us that we actually have 2.7, 3 times the concentration of our potassium ions than we have for our potassium phosphate. And that's because every single potassium phosphate is going to break up to give us 3 potassium ions as it dissociates. So now we see we can use molarity for a variety of different reasons. Conversion factors, how much of an ion is present in solution. We're going to see we're going to use this all the time in lieu of maybe when we would have used molar mass to convert between amount of what we measured, volume, and the number of moles of a solute, and then relate that from like a reactant to a product.